After this lesson, students will be able to determine whether a relation is a function, state the domain and range, and evaluate functions. Do now. Try these 3 questions on your own, so pause the movie and resume when you're ready. Number 1 asks us to evaluate 5 times the quantity of a plus 4 squared when a equals 3. For this question, we just substitute 3 in for a, and then follow the order of operations to simplify. First, we'll do our parentheses, recopy everything else. Next comes our exponents. 7 squared is 49, and since there's no operation in between this number, 5, and the parentheses, that means we're going to multiply 5 times 49. And we get our answer of 245. Number 2, evaluate 40 divided by 5 times 2 plus b cubed when b equals 3. So we begin by substituting 3 in for b. There are no parentheses, so next we do our exponents. And 3 cubed is 27. Recopy everything else. Next comes multiplication and division from left to right. 40 divided by 5 is 8, and then I recopy everything. Next comes multiplication. 8 times 2 is 16 plus 27, which gives us our answer 43. And finally, evaluate the quantity of 6c plus 3 squared when c equals 2. So I have 6 times 2 plus 3, and that entire quantity is squared. Inside the parentheses, we have multiplication and addition, so we begin by multiplying 6 times 2, which is 12, recopying everything. Next comes parentheses. 12 plus 3 is 15, and then we square that to get our answer of 225. A relation is a set of ordered pairs. Only some relations are considered functions. So first we'll begin by graphing this relation. You'll notice how the relation in this case is a set of ordered pairs. In this case we have 4 ordered pairs, and they are enclosed by braces to show that they all do go together on the same coordinate grid. And as you know, ordered pairs have an x and a y coordinate, and it's always x and then y. And we have our x-axis and our y-axis. So now to graph these points, we have -2, 4. So I move -2 on the x-axis and +4 on the y-axis, and that's where that point goes. Then we have 3, -2, so we move 3 on the x-axis and -2 on the y-axis. Next we have -1, 0, so we move -1 on the x-axis and 0 on the y-axis. And finally 1, 5, so we move +1 on the x-axis and +5 on the y. So this is a relation, a set of ordered pairs. The domain is the set of all the inputs, or x-coordinates, of the ordered pairs. The range is the set of all the outputs, or y-coordinates, of the ordered pairs. Find the domain and range of this relation. Well, when we write our domain and range, we are going to write them in these braces. We also write the numbers from least to greatest, and if there are any repeats, we simply write the number once. Now the domain is the set of all the x-coordinates of the ordered pairs. So I can look along the x-axis and figure out, moving from left to right, which would be least to greatest, what the x-coordinates of each of the points are. So notice how this point would have the least x-coordinate, which is -3. Moving along to the right, we have 3 points that all have an x-coordinate of -1. So I just write it down once. And then moving further to the right, we can see that we have 3 points with an x-coordinate of 1. And so we write that down once. Now to do our range, we create our brace, and then we go from least to greatest again. This time, since the range is the set of y-coordinates, we're going to look along our y-axis, and to move from least to greatest, we have to start from the bottom of our grid and work our way up. So at the very bottom, we have 2 points with a y-coordinate of -4, so we write that down once. Moving upward, we have 1 point with a y-coordinate of -2. Then we have 3 points that have a y-coordinate of 1, so we write it down just one time. And then finally, we have a point with a y-coordinate of 3. So again, our domain is the set of all of the inputs or x-coordinates of the ordered pairs, so we looked along the x-axis for those, and our range is the set of all the outputs or y-coordinates of the ordered pairs, so we looked along our y-axis for those. Now let's talk about mapping diagrams. In order to create a mapping diagram, write the elements of the domain in one region and the elements of the range in another. Draw arrows to show how each element from the domain is paired with elements from the range. So we'll begin. You can write either input and output or domain and range. Either one works. They are synonyms. And just like we did before, we're going to arrange the input and output values from least to greatest, and we're going to write each one only once. So looking for our inputs, we look for all the x-coordinates, -1, 3, -5, and 3. Now our smallest input value is -5, so I'm going to put that first, followed by -1. And then we have 2 input values of 3, but we're just going to write it down once. Then we do the same for our output. We have -2, 6, -10, and 2. From least to greatest, that would be -10, -2, 2, and 6. Now we draw arrows to show how each element from the domain is paired with elements from the range. So -1 is paired with -2, so we draw an arrow going from our input to the appropriate output. Then we have 3, which leads us to 6, so we draw an arrow from our input 3 toward our output of 6. And then we go from -5 to -10. And finally, we have the input 3 again, and this time the output is 2, so we do have 2 arrows originating from the 3, 1 to the output of 2 and 1 to the output of 6. And this is a mapping diagram for this relation. Now you try the next one, so pause the movie and resume when you're ready. In this example, we again write our input and output, or domain and range, whichever you prefer. And we go from least to greatest with our input or x-coordinates. So we have -1, 1, 1, and -1. So basically the only 2 inputs we have are -1 and 1, which I write from least to greatest. Our outputs are 7, 3, 7, 3. So again, it's just those 2, 3 and 7. We'll write it from least to greatest. Then we draw our arrows. -1 to 7, 1 to 3, 1 to 7, and -1 to 3. You may recall from years past learning about something called a function machine. From what you may recall, a function machine is a machine that has a specific rule, such as x plus 5. Your input is the number that you're substituting in for the variable. So if I have an input of 2 and my rule is x plus 5, then the machine will calculate 2 plus 5 and spit out 7, which is our output. Notice how a function machine can only have one rule. Every time that I input a 2, the only thing that can possibly come out of this function machine is 7, since 2 plus 5 is always 7. In other words, a function, every input can only have one output. So a function is a rule that creates a relationship between the inputs and outputs. For every input, there can only be exactly one output, just like we saw with our machine. Every time we input 2, the only thing that comes out can be a 7. Now, two different inputs can share the same output. So, for example, our input here of 2 will spit out an 8, and then an input of 3 can also spit out an 8. And that is okay because there are some function rules where that will be a possibility, where two different inputs can share the same output. So that is still considered a function. However, two of the same inputs cannot share different outputs. So sometimes when I input a 2, if the machine spits out a 7, and then other times if I input a 2 and it spits out an 8, then that is not actually a function. The function machine would be broken. So two of the same inputs cannot share different outputs. So pause the movie and decide whether or not the following are functions. Resume when you're ready. In our first example, we notice that there is the input 3 that sometimes gives an output of 7 and an input of 3 that sometimes gives an output of 8. Since every input can have only one output, this is not a function. Number 2, 1, 2, 3, and 4 all give outputs of 18. Different inputs can share the same output as long as every time I input a 1, it spits out an 18, and every time I input a 2, it spits out an 18, etc. So this is considered a function because each input has only one output. And then finally, in our last example, none of the inputs overlap, and all we can see is that each input does have its own unique output, and so therefore this is a function. State whether the following relation is a function. If it is not a function, state why. You may want to use a mapping diagram. Feel free, if it helps you to visualize, to always create a mapping diagram. Otherwise, you can just look and analyze each of the inputs, see if any of those are repeats, and if they are, figure out if they give the same output each time or different outputs. For number 1, our inputs are 5, 2, -1, and 3. Since none of our inputs overlap, each time we have an input of 5, the only output that we see here is -3. Each time we input a 2, it gives a 4. Each time we input a -1, it gives a 6, and each time we input a 3, it gives a 7, as far as we can tell. So according to this relation, it is a function. You try number 2. Pause the movie and resume when you're ready. Number 2, you'll notice that the input 3 sometimes gives an output of 4 and sometimes gives an output of 2. So this is not a function. The reason why is because the input 3 has more than one output. If you are given a graph and not just a table or the ordered pairs, you can use something called the vertical line test to help you determine whether or not the relation is a function. Since each input can have only one output, that means that every x-coordinate can only have one corresponding y-coordinate. If an x-coordinate has more than one y-coordinate, then you would have points that are exactly vertical from one another. So you can use this vertical line test. So by drawing vertical lines and visualizing what that would look like, see if there is any point where the graph crosses the vertical line more than once. In this case, no matter where I draw vertical lines, the graph would only touch it one time. Therefore, this is a function. Number 2 is also a function. No matter where I draw a vertical line, the graph will only touch once. Some students get a little confused down here where it looks like it starts to go vertically, but this graph is gradually moving to the left, and therefore there are no points, no x-coordinates that have exactly the same y-coordinate. So yes, this is a function. Try the remainder of this slide on your own, so pause the movie and resume when you're ready. In our third graph, this is not a function. If I were to draw a vertical line here, the graph would cross that vertical line twice, once up here and once down here. Since this input or x-coordinate has more than one y-coordinate, this is not a function. Again, with this graph, this does not pass the vertical line test. For example, the x-coordinate 0 would cross up here, again here, and over here. So there are 3 different outputs for an input of 0. Therefore, this is not a function. And finally, in our last graph, even though the dots are not connected, you still need to analyze if it will pass the vertical line test no matter where I look on the coordinate grid. Notice how over here we have 2 points that are vertical from one another, and therefore this is not a function. Now let's talk about function notation. To change an equation to function notation, change the y when the equation is in slope-intercept form to f of x. Notice how this is pronounced f of x, not f times x. Also note that sometimes a g of x or h of x may be used to show 2 or 3 different equations in the same problem. F of x does not mean f times x. Instead, it indicates that the equation is a function, meaning that once I were to graph this, it would pass the vertical line test, that each input or x-coordinate has exactly one output or y-coordinate. If you have a statement such as f of 2 equals 11, this means that when I have an input of 2, the function machine will spit out an output of 11. So f of 2 equals 11 means that the output is 11 when the input is 2. In f of negative 5 equals negative 17, this means that the output is negative 17 when the input is negative 5. Evaluate the function when x equals 2, x equals 0, and x equals negative 3. In our first example, f of x equals 10x plus 1. All this means is that it is a function and that the rule of the function machine is 10x plus 1. F of 2 is asking for the output when the input is 2. So if you think of a function machine with the rule 10x plus 1 and an input of 2, all you would need to do is plug in, we'll do it over here, 10 times 2 plus 1, which equals 20 plus 1, or 21. F of 0, we input a 0 into our function machine. So 10 times 0 plus 1, 0 plus 1 is 1. And finally, f of negative 3, we're going to input negative 3 into our function machine, and we get negative 30 plus 1, or negative 29. You try number 2 on your own, so pause the movie and resume when you're ready. In this case, we have h of x equals 3x plus 6. H of x tells us that it is a function and that the rule is 3x plus 7. H of 2 is asking for the output when the input is 2. So we substitute 2 in for x and simplify. 6 plus 6 gives us 12. So the output is 12 when the input is 2. H of 0, we substitute 0 in for x, and we get that h of 0 is 6, or the output is 6 when the input is 0. And finally, we input our negative 3, and we find that the output is negative 3 when the input is negative 3. Now let's make a table for f of n equals negative 2n squared plus 7. Use 1, 2, 3, and 4 as domain values. As you recall, domain is the set of the input or x coordinates. So we're going to substitute 1, 2, 3, and 4 in for n. This is our function rule. So now all I need to do is substitute those values in for n and simplify in order to find the output. So we have negative 2 times 1 squared plus 7. Follow the order of operations. 1 squared is 1, times negative 2 is negative 2, plus 7 gives us 5. When I input a 2, we start with our exponents. This gives us 4 times negative 2 is negative 8, plus 7 is negative 1. Next, we input a 3. Do the exponents first. 3 squared is 9, times negative 2 is negative 18, plus 7 is negative 11. And finally, input 4. 4 times 2 is 16, times negative 2, which is negative 32, and negative 32 plus 7 is negative 25. Evaluate the function rule f of a equals negative 3a plus 5 to find the range of the function for the domain negative 3, 1, 4. This is very similar to the problem that we just did, but they just didn't give us a table to fill out. They are telling us that the domain or x coordinates or input values that we should use are negative 3, 1, and 4, that it is a function, and that the rule for that function machine is negative 3a plus 5. So we'll begin by finding f of negative 3 by substituting in negative 3 for a. Negative 3 times negative 3 is positive 9, and f of negative 3 is 14. Now keep in mind that this means f of negative 3, not f times negative 3. A common mistake when people are first learning this is to want to now divide both sides by negative 3 in order to isolate an f, but that is not what we are doing here. This is a notation for a function rule. So f of negative 3 we found to be 14. We repeat that process for input values of 1 and for 4. So f of 1 equals negative 3 times 1 plus 5. F of 1 equals negative 3 plus 5. So f of 1 equals 2. And finally, f of 4, we're substituting 4 in for a. Now that we found the output values that correspond to those input values, we're going to write our domain in our braces from least to greatest. So negative 7, 2, and 14. Now you try the next one on your own. Pause the movie and resume when you're ready. Find the range of the function f of x equals x squared plus x minus 6 for the domain negative 2, 0, 5. Let's begin by finding f of negative 2 by substituting negative 2 in for x. Notice how the x is being squared. So when I substitute in negative 2, that is being squared. So it needs to be in parentheses. That is very important. So be sure to put that in parentheses. Plus our x, which is just negative 2, minus 6. Now the reason it's so important that it's in parentheses, if you recall from earlier chapters, is that negative 2, the whole quantity, is being squared. So we do negative 2 times negative 2, which gives us positive 4. Had we not put them in parentheses, then we would have gotten negative 4. So it does make a big difference. Now we go from left to right, so 4 plus negative 2 gives us 2 minus 6, and we get that f of negative 2 is negative 4. Now let's do 0. Since we don't have a negative number, we didn't have to put it in parentheses here. 0 squared is 0, plus 0, minus 6 gives us negative 6. And then finally, f of 5, we plug in 5, and we get 25 plus 5 minus 6, 30 minus 6, so f of 5 is 24. And then our answer we put in braces from least to greatest, so negative 6, negative 4, and 24. Now let's try graphing the function f of x equals negative 2x plus 5. We can start by creating a table. Our input is x, our rule is negative 2x plus 5, and then our output is f of x. Now this problem does not specify what input values or domain values we should use, so a good rule of thumb is to use negative 2, negative 1, 0, 1, 2, and then we can plug those values in for x. Negative 2 times negative 2 is positive 4, plus 5 is 9. Plug in negative 1, and we get 2 plus 5 or 7. Plug in 0. 0 plus 5 is 5. Plug in 1. Negative 2 plus 5 is 3. And finally, plug in 2. Negative 2 times 2 is negative 4, plus 5, which is 1. Now, x is our input values, or x values, and our f of x is our output values, which are the y coordinates. So, we could write ordered pairs now from this table. Negative 2, 9, because when I have an input of -2, I have an output of 9. -1, 7, 0, 5, 1, 3, and 2, 1. And now we plot those ordered pairs. -2, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's off this grid. -1, 7, -1, 1, 2, 3, 4, 5, 6, 7. 0, 5, 1, 3, and 2, 1. Notice how this makes a line. And we can go ahead and connect this with a straight edge. And we draw arrows on either end.